Welcome to the DX Today podcast, your daily deep dive into the AI ecosystem. I'm Chris, and joining me as always is Laura.
Thanks, Chris. And I am genuinely thrilled about today's story because it sits right at the intersection of artificial intelligence, hard fundamental physics, and one of the most consequential supply chain vulnerabilities quietly threatening the entire modern electrified economy that most people never really think about.
You have my full attention already, but let's ground our listeners before we dive deep. When you put supply chain vulnerability and fundamental physics in the same sentence, what exactly is the piece of technology we are actually talking about here today?
We are talking about permanent magnets, those unglamorous but absolutely essential components hiding inside electric vehicle motors, wind turbine generators, computer hard drives, missile guidance systems, MRI machines, and basically every single device that quietly converts electrical energy into physical motion around us.
And I'm guessing the reason this suddenly became newsworthy is not the humble magnet itself, but rather the fact that scientists are now deploying artificial intelligence to design entirely new versions of them without relying on the usual troublesome ingredients.
Exactly right. Researchers at Ames National Laboratory out in Iowa, led by a material scientist named Prashant Singh, just published what they call an AI-driven roadmap in the journal Advanced Functional Materials for Designing Powerful Permanent Magnets that contain no rare earth elements whatsoever.
Before we get to the clever artificial intelligence part, help me understand the villain lurking in the story. Why are rare earth elements such a persistent problem that scientists and governments would actively want to eliminate them from these magnets entirely?
The problem is not that rare earths are physically scarce in the ground. It is that the supply chain sits dangerously concentrated in one place. China mines roughly 60% of the world's rare earths, but processes about 90% and manufactures around 94% of the finished magnets.
Those numbers are genuinely staggering once you actually sit with them for a moment. So essentially, one single country holds a near total monopoly over a material that simultaneously powers electric cars, renewable energy infrastructure, and virtually every modern defense system on the entire planet.
That is precisely the strategic vulnerability everyone is worried about right now. For the heavy rare earths like dysprosium and terbium, China controls somewhere around 98 to 99% of global separation capacity, and just last year, the United States remained 67% reliant on imports for most of these elements.
Okay, so the strategic motivation here is obvious and frankly rather urgent. Now walk me carefully through what the Ames Lab team actually did differently, because using artificial intelligence to discover new materials is not, by itself, a completely brand new idea in this field, is it?
You are right that AI for materials discovery is not remotely new, but the crucial distinction here is that most previous systems were trained purely on large databases of materials that human scientists had already discovered, characterized, and painstakingly cataloged over many previous decades of laboratory work.
And I assume the fundamental limitation of that older approach is that a model trained only on things we already happen to know tends to simply remix and recombine the past, rather than inventing something genuinely unprecedented that nobody has ever seen before anywhere.
You have put your finger squarely on the bottleneck. A purely data-trained model essentially interpolates between the known examples it was fed, so it fundamentally struggles to leap into whole regions of chemistry that no human has ever recorded in any existing scientific database anywhere on Earth.
So what precisely is the alternative that the Ames team is championing here? And why do they believe that baking actual physical law directly into the model changes the entire game so fundamentally compared to that older, purely data-driven way of working?
Their approach fuses physics-based modeling together with high-throughput computational simulations and newer reasoning-based AI tools. So the system genuinely understands how electrons actually behave inside a material, rather than merely memorizing surface-level patterns from some fixed catalog of previously published experimental results.
Let's try to make that concrete for the many people who did not spend their weekends studying quantum mechanics in graduate school. When you say the model understands electrons, what specific physical properties is it actually calculating and predicting for each candidate magnet that it considers?
Two properties matter most for any permanent magnet, and this model computes both of them directly from first principles physics. One is called magnetocrystalline anisotropy, which keeps the magnetization stubbornly locked in a single stable direction, and the other is the material's all-important Curie temperature.
Before we get to the clever artificial intelligence part, help me understand the villain lurking in the story. Why are rare earth elements such a persistent problem that scientists and governments would actively want to eliminate them from these magnets entirely?
Curie temperature is simply the heat threshold above which a material abruptly loses its magnetism entirely. So, if your magnet is going to sit inside a hot, hard-working electric motor for years on end, you desperately need that particular number to be comfortably and reliably high.
That makes perfect intuitive sense, and it neatly explains why you cannot simply grab any old magnetic metal off a shelf and expect it to work. The AI essentially has to balance several demanding physical properties all at once before anyone even bothers physically building the thing.
Precisely, and that is exactly where the real computational power lives. The system rapidly screens enormous numbers of candidate chemical compositions entirely inside the computer, ranking them by these physics-based properties so that researchers ultimately only synthesize the tiny handful of most promising options in an actual laboratory.
Now, I want to deliberately put on my skeptic hat for a moment, because whenever I see breathless headlines screaming that artificial intelligence has just single-handedly solved some decades-old materials science problem, my very first instinct is always to ask exactly where the hidden catch is.
And you absolutely should ask that because honestly, some of the recent media coverage has raced well ahead of the actual underlying science, and there are serious, credentialed researchers out there pushing back quite firmly against the more breathless and exaggerated magnet headlines currently making the rounds.
So please lay out the counter-argument as fairly as you possibly can for me. When these thoughtful critics essentially say, not so fast, what exactly are they pointing to as the real gap between an exciting press release and genuine hard commercial reality on an actual factory floor?
The core critique is that none of these AI-designed candidate materials has yet actually demonstrated a true drop-in replacement for neodymium iron boron, which stubbornly remains the industry gold standard. So realistically, we are still sitting very early on the overall technology maturity curve here.
In other words, we are currently somewhere near what industry analysts might politely call the technology trigger stage, where the underlying science is genuinely promising and real, but actual commercial products manufactured at serious industrial scale are still very much several years down the road ahead of us.
That is a completely fair characterization, and it is genuinely worth stating plainly that discovering a promising candidate material inside a computer simulation is a fundamentally different achievement from reliably manufacturing many millions of durable, high-quality magnets at a genuinely competitive cost out in the real world.
But there is at least one notable real example that seems to partially bridge that daunting gap between an abstract simulation and something you can actually physically hold in your own hand, isn't there? Coming out of a company over on the other side of the Atlantic?
Yes, there genuinely is. A British deep technology firm called Materials Nexus used its own proprietary AI platform to rapidly sift through more than 100 million possible chemical compositions and eventually landed on a genuinely promising, rare, earth-free magnet that they went on to name MagNex.
100 million separate compositions is frankly a number that no human research team could ever realistically grind through by hand across several entire lifetimes of patient work. So what did all of that raw computational firepower actually buy them practically in terms of pure development speed?
They took roughly just 3 months in total to design, synthesize, and physically test the new material, which the company estimates is somewhere around 200 times faster than the traditional slow trial and error path that material science has historically been forced to rely upon for generations.
Raw speed is certainly impressive on its own, but you and I both know perfectly well that a mere laboratory curiosity only truly matters commercially if the underlying economics actually work out cleanly. Did the MagNex numbers genuinely look attractive on both cost and environmental impact as well?
They genuinely did look attractive, at least on paper so far. The company claims that MagNex can be processed at roughly 20% of the cost of a comparable rare earth magnet, while simultaneously cutting the associated manufacturing carbon emissions by somewhere around a rather remarkable 70%.
Those particular figures are certainly compelling, though I will freely admit I would personally want thorough independent verification before betting an entire factory on them. Still, it raises a much deeper question that I keep circling back to. Why exactly are rare earths so uniquely good at this specific job?
It ultimately comes down to a genuinely deep quirk of atomic structure itself. Rare earth atoms like neodymium possess these deeply buried inner 4f electron orbitals that generate exceptionally strong magnetic anisotropy. And honestly, that specific property turns out to be remarkably hard to convincingly replicate with anything else.
So when a physics-informed AI system tries to cleverly design its way around rare earths, it is essentially searching for some ingenious architectural trick to mimic a valuable property that nature simply handed those particular elements almost entirely for free through pure atomic luck.
That is a genuinely lovely way to frame the whole challenge. The AI is essentially hunting for structures and element combinations where cheap, abundant, ordinary materials, when arranged in exactly the right crystalline geometry, can collectively imitate what a single rare earth atom manages to do all by itself naturally.
Let's deliberately zoom out to the broader national security dimension for a moment. Because this clearly is not merely some abstract academic exercise about elegant chemistry for its own sake. There are serious governments and militaries around the world watching this specific line of research extremely closely, correct?
Absolutely. And this specific piece of work is actually part of the Department of Energy's newly announced Genesis mission, which very deliberately unites the national laboratories, private industry, and universities together to aim artificial intelligence squarely at energy, fundamental discovery science, and critical mineral security all at the same time.
It is genuinely fascinating that the government is now openly framing artificial intelligence, not merely as a clever chatbot or a convenient office productivity tool, but explicitly and deliberately as a serious scientific instrument for solving strategic materials problems that directly threaten national resilience and long-term security.
And notably, they are not putting all of their eggs in one single methodological basket either. A startup memorably called Alice and Bob very recently secured a substantial multi-million euro government research award specifically to attack this very same stubborn magnet problem, except using quantum computing instead of classical AI.
So we now have physics-informed classical AI running on one track and full quantum computing running on another entirely separate track, both racing hard toward the exact same ultimate goal of freeing critical technologies from a single dominant foreign supplier. That is honestly quite a remarkable convergence to witness.
It really genuinely is, and I honestly think the deeper story here actually transcends magnets entirely. This exact same physics-informed philosophy is now quietly showing up all across materials science, including a closely related sibling model specifically built to predict ductility in the alloys destined for fusion reactors and aerospace.
That particular sibling model detail is genuinely intriguing to me because it strongly suggests that we are actually watching the early birth of an entire new category of tools, rather than just one isolated lucky result. So, what exactly unites all of these physics-grounded systems together in your own mind?
What fundamentally unites them all is a genuine philosophical shift away from purely data-hungry models that desperately need enormous mountains of prior examples, and toward models that actually carry the real laws of nature inside themselves, and can therefore reason intelligently about the genuinely and completely unknown.
I personally find that particular shift genuinely profound, because so much of the current public conversation about artificial intelligence fixates almost entirely on language and images, while this much quieter revolution in scientific modeling could realistically reshape entire physical industries over the coming decades in ways we barely even notice.
Exactly. And it also meaningfully reframes what we should even reasonably expect from artificial intelligence in the very first place. Instead of a system that merely dazzles us with fluent text, we get a patient, tireless collaborator that intelligently narrows an impossibly vast search space down for the human experts.
Before we wrap up today, let me try to honestly hold both competing truths at once, because I genuinely think that is the intellectually honest posture to take here. This is real, seriously fundable, rigorous science, and yet simultaneously it is absolutely not a finished product sitting on store shelves tomorrow morning.
That careful balance is exactly right, and I would genuinely tell any listener out there to stay excited, but also stay genuinely patient. The long path from a promising computer simulation to an actual magnet physically spinning inside your next electric car remains long, expensive, and honestly still quite uncertain today.
And yet, given that global rare earth demand is currently projected to roughly triple within just the coming decade, even a modest, partial success in this particular line of research could meaningfully relieve enormous strategic pressure on a dangerously strained and overly concentrated global supply chain that ultimately affects everyone.
That is honestly the entire stakes captured in a single sentence, and it is precisely why I personally will be watching Ames Lab, Materials Nexus, and every other serious research team working in this crowded space with real, genuine fascination over all of the many months still ahead of us.
Well, if nothing else at all, I sincerely hope our listeners walk away today clearly understanding that some of the most genuinely important artificial intelligence work happening anywhere right now has absolutely nothing whatsoever to do with writing routine emails or generating pretty pictures on a screen.
I honestly could not have possibly said it any better myself. The real frontier of applied artificial intelligence increasingly runs straight through quantum physics, materials chemistry, and the profoundly unglamorous magnets that quietly and faithfully hold our entire electrified modern civilization together every single ordinary day.
That's all for today's episode of the DX Today podcast. Thanks for listening, and we'll see you next time.